Welcome back to the Deep Dive. Today, I want to take you to the absolute edge of the world. We are traveling, mentally, at least, to the Atacama Desert in Chile. It's high, it's incredibly dry, and it's arguably the best place on planet Earth to look at the stars.
It really is an astronomer's paradise. And we're going to a specific spot, the La Silla Observatory, to look at a very specific piece of machinery, the Swiss 1.2-meter Leonhard Euler telescope.
Now, usually when we talk about telescopes on this show, we're talking about the flashy stuff, what they found, new galaxies, black holes, that kind of thing.
The discoveries.
But today, we're doing something different. We're looking at a master's thesis that asks a question that I honestly never thought about before, but now that I've read this, it's kind of driving me crazy.
It's a fundamental engineering question. The thesis is titled Automatic Pointing Model for Euler, and it was written by a student at the University of Geneva named Nota Albert Einstein.
And yes, we have to address the elephant in the room right away. The name, Nota Albert Einstein.
I know. If you are going to write a thesis in a physics department, that is a very heavy last name to carry.
Talk about pressure. But looking at the source material, the work really stands on its own. It's a rigorous look at a problem that sounds so simple, but is actually a nightmare.
Well, what is the core question?
How does a massive, multi-ton metal telescope actually know where it's looking?
It sounds like such a trivial question, doesn't it? You have a motor. You have a map of the stars. You just tell the motor, go to star X. Why is that hard?
Exactly.
Yeah.
My phone knows where it is. My car knows where it is. Why doesn't this giant, expensive telescope know where it is?
Well, your phone isn't trying to hit a target the size of a coin from 5 miles away while sitting on a spinning merry-go-round.
Okay, let's unpack that analogy because that's the image that really stuck with me. We are on a spinning planet.
Right. The Earth is rotating at 1,000 miles an hour, so the ground is constantly moving. That's challenge one. But challenge number two is the telescope itself.
It's just a huge piece of metal.
A huge structure of steel and glass. And we tend to think of metal as, rigid.
Like a rock.
But at this scale and with this level of precision, metal isn't rigid at all. It's elastic. It expands when it's hot, contracts when it's cold, and most importantly, it bends under its own gravity.
So the telescope is actually sagging.
Constantly. And the sag changes depending on where it's pointing. If it's pointing straight up, it sags one way. If it's pointing at the horizon, the nose of the telescope just dips.
So pointing isn't just aim and shoot. It's a constant battle of compensating for a flexible machine on a spinning rock.
And this thesis is essentially about upgrading the brain of that telescope to handle that battle better. Specifically, moving from an old sort of manual workflow to a new automated Python-based system.
Let's get into the hardware first, because the sources describe the Euler telescope as having an Alt-Az mount. I know that's standard jargon for you, but break that down for us.
Okay, Alt-Az just stands for altitude azimuth. It's the most intuitive way to build a mount. You have one axis that goes up and down, that's altitude, up and down.
Got it.
And you have another axis that spins left and right, that's azimuth.
Okay, so like a tank turret or, a camera tripod.
Exactly like a tank turret. It's mechanically very stable, it's compact, and it's cheaper to build for large telescopes because gravity is always pulling straight down through the base.
But wait a second. Stars don't move like tank turrets. They don't go up and left. They arc across the sky because of the Earth's rotation.
And that is the problem. The natural way to build a telescope is what's called an equatorial mount. You actually tilt the whole machine so one axis aligns perfectly with the Earth's axis.
So it moves with the stars.
Yes, to track a star, you just spin one motor at a constant speed. It's very elegant. But an equatorial mount for a 1.2-meter mirror would be massive, heavy, and incredibly expensive.
So they went with the tank turret, the Alt-Az.
They did. But the trade-off is that the software has to work much, much harder. It has to constantly move both motors to mimic that arc. It has to step up and left thousands of times.
And there's an even deeper issue, right? Something called field rotation.
Yes. This one is tricky to visualize. Imagine you're looking through the tank turret at a painting on the wall. If you rotate the turret left, the painting stays upright, right?
Sure.
But if you're tracking a star across the sky with an Alt-Az mount, the geometry gets weird. The star stays in the center of your view, but all the other stars around it appear to slowly spin in a circle during the night.
So the image is rotating inside the camera.
Exactly. So not only do you need motors to point the telescope, you need a third motor to physically spin the camera to keep the picture upright. It's a complex dance.
And if any one of those dancers steps on a toe, you miss your target.
You miss the star.
Yeah.
This brings us to the enemy of the thesis, pointing errors.
The paper breaks them down into geometric errors and physical realities. Let's start with geometry. What does it mean for a telescope to have geometric errors?
It means the machine isn't a perfect shape. The thesis mentions NPAE, non-perpendicularity. In a perfect world, the up-down axis and the left-right axis are exactly 90 degrees apart.
But in the real world,
Maybe they're 89.9 degrees or 90.01. And that tiny fraction means when you tell the telescope to go west, it actually goes west and a tiny bit south.
I'm guessing that error just gets worse the further you move.
It compounds. Plus, the whole mound might be tilted. It might be leaning slightly north. These are static errors. They don't change much, so you can measure them and subtract them.
But then you have the physical realities, and the one that really blew my mind was tube flexure. This is literally the telescope bending under its own weight.
It is. The Euler telescope is a long tube with a heavy 1.2-meter mirror at the bottom and another mirror at the top. When it points straight up to the zenith, gravity pulls straight down. It's symmetrical.
But as soon as you lower it toward the horizon,
Gravity pulls on the side of the tube. The nose dips.
how much of a dip are we talking about? Like inches?
Physically. Oh, maybe a fraction of a millimeter. But that tube is a long lever, and you're magnifying the sky thousands of times. That tiny physical sag translates to a huge error on the sky.
So the model has to predict the sag before it happens.
Precisely. It's anticipating the failure of the metal. And then, just to make things harder, the air itself gets involved. Atmospheric refraction.
Like a spoon in a glass of water.
Exactly. The atmosphere acts like a lens. A star near the horizon looks higher than it actually is because the light bends. The model needs to know the air pressure, the temperature. It all changes the equation.
So this pointing model we keep talking about, it's not a map, it's a live filter.
It's a translation layer. The astronomer says, go to star A, and the model intercepts that and says, actually go a little left because the axis is crooked, a little up because the tube is sagging, and a bit lower because the air is thick tonight.
Now, why does this matter so much for this telescope?
Yeah.
The thesis talks about two instruments, ECAM and Coralie. And they seem to have very different needs.
Very different. ECAM is the camera. It has a relatively wide field of view, about 15 by 15 arc minutes.
So if you miss by a tiny bit, the star is probably still in the picture somewhere.
Right. It's forgiving. You can just crop the image later. But Coralie is the diva.
The high-maintenance instrument.
Coralie is a spectrograph. It's used for finding exoplanets. It doesn't take a picture. It analyzes the light spectrum. To do that, all the starlight has to be focused into a single optical fiber.
And how big is that target? I want you to give the listener a sense of scale.
The fiber has an aperture on the sky of just 2 arc seconds.
2 arc seconds.
If the pointing is off by 3 arc seconds, which is nothing, it's less than a hair's width at arm's length. The starlight just hits the metal rim around the fiber.
And you get 0 data.
You get darkness. You get nothing. For Coralie, accurate pointing isn't a luxury. It's a hard requirement for the instrument to even function.
So how did the student, Nuda, go about building this new model? The thesis describes collecting a ton of data.
To build a map of the errors, you have to test the telescope. You create a grid of stars covering the whole sky, tell the telescope, go look at these 50 stars, and then you measure exactly how far off it was for each one.
And this is where the student got a little creative. They didn't just use a standard grid. They tried a Fibonacci lattice.
Yes, this was a fascinating detail. The Fibonacci lattice is based on the golden ratio. You see this pattern in nature, sunflower seeds, pine cones. Nature uses it to pack things perfectly uniformly on a sphere.
So the thinking was, if it works for sunflowers, maybe it works for the sky.
Exactly. The hypothesis was that a Fibonacci grid would give perfectly uniform test stars, which might create a better model.
I love that. Nature meets astrophysics. Did it work?
It worked. Fine. It wasn't worse. But the thesis found the standard spiral method, which starts at the top and spirals down, worked just as well, and maybe even a little better.
So why stick with the spiral?
It turns out the spiral naturally puts a few more points near the zenith, straight up. And having more data up there is actually really helpful for figuring out the tilt of the whole telescope. So the old way won out.
Sometimes the standard is standard for a reason. Speaking of the old way, let's talk about calibrating Coralie. The thesis describes this legacy workflow, and it sounds painful.
Oh, it was a mess. It was a classic bootstrap problem. Usually to calibrate, you wipe the memory and start fresh. But for Corley, if you wipe the memory, the pointing would be so bad you'd never land the star on the fiber.
You'd be totally blind.
Exactly. So they had to keep an old, partially broken model running just to get the star near the fiber. Then they'd take a picture, manually measure the offset on the screen, literally counting pixels, and do the math.
That sounds incredibly slow and prone to error.
It was. And this is where the Euler-J project comes in, the modernization. They switched to something called plate solving. This seems like the magic bullet in the thesis.
Oh, plate solving. So what is that?
It's basically facial recognition, but for the sky. The telescope points anywhere and takes a picture. The computer analyzes the pattern of stars, the geometry, the distances. Then it compares that pattern to a massive database of the entire known universe.
It's fingerprinting the sky.
Instantly, it finds a match and says, aha, this pattern of stars only exists at these exact coordinates. So the telescope can be totally lost, take one picture, and the software says, you are here.
That's a huge leap forward. No more counting pixels.
No more. It lets them use the same automated approach for both the easy camera and the hard spectrograph.
Now, there's a part of the thesis that reads like a detective story. While they were building this, the student noticed something was wrong. The pointing for Corley was just erratic.
Yes, this is the part every engineer will relate to. The data looked wrong, the telescope was jumping around, the math should have worked, but the machine wasn't behaving.
So what did NUDA do?
They decided to audit the transformation matrix.
Okay, that sounds impressive. What is it?
It's the piece of code that converts pixels into motors. If the camera sees the star is 50 pixels to the right, the matrix tells the motors exactly how many degrees to spin.
And what did they find?
It was wrong. The numbers in the code didn't match the physical reality of the telescope. It was a legacy setting that everyone just assumed was correct because, it's always been that way.
So for years, the telescope had the wrong settings.
Likely, yes. The student ran a new test, moved the telescope a specific amount, measured the pixel shift, and recalculated the matrix from scratch.
And the result?
Boom. Immediate stability. The erratic behavior just vanished. It's a great lesson. Check your constants. Just because a number is in the code doesn't mean it's right.
I love that. So they've fixed the matrix, they have plate solving. Now comes the main event. The student's new software versus the industry heavyweight.
In the red corner, we have TPOINT.
TPAIT.
It's the gold standard used by huge observatories like Keck and Gemini. It's incredibly powerful, but it's proprietary. It's closed source. You have to pay for it. And it's written in C, which makes it hard to integrate with modern Python scripts.
And in the blue corner,
the student's custom Python framework built from scratch for this thesis using least squares optimization.
Which is basically just finding the line of best fit through all that error data, right?
Essentially, yes. It's a way to find the formula that minimizes the error across all those test stars.
So who won?
It was a draw, and that is a massive victory for the student.
A draw is a win here because one is free and open, and the other is expensive and closed.
Exactly. They ran both models on the same data. The thesis shows these residual maps of the errors left over. They looked nearly identical.
Give us the numbers. How precise are we talking?
For the eCam camera, the student's Python model had an error rate, an RMS, of about 1.82 arcseconds. TPOINT was also 1.82.
Identical.
And for the difficult one, Corley, using the new plate solving method, the Python code got the error down to 1.46 arcseconds.
1.46 arcseconds. Can you contextualize that for me?
An arcsecond is roughly the width of a dime seen from 2 miles away.
That is just absurd precision.
It is. And remember, this is a multi-ton machine fighting gravity and wind. Getting the error down to that level is an engineering triumph. The custom Python code works just as well as the industry standard, but it's free, open source, and fits perfectly into their new system.
There was one more test that I found really clever, the star elongation test. This feels like the ultimate proof.
It is. It's one thing to find a star. It's another thing entirely to keep it.
Because the Earth keeps spinning.
Right. So they pointed the telescope at a star and took a 5-minute exposure. If the model is bad, the telescope will drift slightly. The star in the photo won't be a sharp dot, it'll be a smear, an oval.
You want a dot, not a dash.
Precisely. And the result. The stars were perfectly round, the elongation factor was less than 0.1. The model isn't just pointing, it is tracking. It's fighting Earth's rotation and the tube flexure in real time, and it's winning.
However, there was one area where the model and the telescope itself sort of admitted defeat. The zenith.
Ah, yes, the blind spot.
Both models, TPO-AIM-T and the new Python one, struggled when the telescope looked straight up. Why is straight up so hard?
It's a mathematical singularity. We talked about the alt-az, mount, altitude, and azimuth. When you point straight up to 90 degrees altitude, what happens to azimuth?
I guess. Every direction is south. It's undefined.
Exactly. If a star passes directly overhead, the azimuth motor would have to spin infinitely fast to turn the telescope around to follow it. The math just blows up.
Like dividing by zero.
The polynomial terms in the equation become unstable. So the thesis notes that the telescope effectively has a no-fly zone. It just avoids looking at stars above 85 degrees elevation.
So don't look up, at least not straight up.
Right, you just have to wait for the star to move a little lower before you observe it.
So let's zoom out. We have a verified model. The code works. This isn't just some theoretical paper, is it?
No, and that's the best part. This code is live. It is running on the Euler telescope right now. Every night, when that dome opens in Chile, Newton's code is steering the ship.
So why does this matter for the listener? We aren't all operating giant telescopes in the desert. Why should we care about pointing models?
It matters because of efficiency. We're in a golden age of finding exoplanets. Missions like the TESS satellite are finding thousands of candidates. But TESS just finds blips.
It finds the maybe.
Exactly, it finds the maybe. Ground-based telescopes like Euler have to confirm them. They have to stare at those stars for hours to prove a planet is really there.
And if you spend 20 minutes of your precious night just trying to find the star,
that's 20 minutes of lost science. Multiply that by every night, every year. Better pointing means less wasted time, which means more data, which means more confirmed planets. This thesis directly contributes to our ability to map the universe around us.
it really highlights that modern astronomy isn't just about polishing mirrors. It's about code. It's about math fighting physics.
That's a great way to put it. We often think of astronomy as looking at the stars. But this deep dive shows half the battle is looking at the machine. Fighting gravity, fighting temperature, fighting the way metal bends. If that 1.2-meter mirror sags by a fraction of a millimeter, you lose a whole planet.
The hitter math holding up the sky.
It's the infrastructure of discovery.
So, here's a provocative thought to leave you with. We trust our GPS to tell us where we are within a few meters. We trust our phone cameras to autofocus instantly. But behind those simple interfaces is a war being fought against geometric errors and physical realities, just like in this telescope. What other invisible correction models are running in your life right now, keeping you pointed in the right direction without you even knowing it?
Something to think about.
Thanks for listening to The Deep Dive. We'll see you on the next one.